Okay, good morning, everyone. Questions as usual? Any questions about the homework? Number 99. Okay, we look at that. Number 99. Okay, so we have an object which is moving along a line, and we are given the following, that the acceleration is 0.2 t, and the velocity at t equal to 0 is 0, and the initial position at 0 is 0. Okay, so we have this object moving, and we know how the acceleration, it means we know how fast the velocity is changing, and we have to know exactly where is the object is, the position of the object at every time t. Okay, so it's basically what we did yesterday, but with a certain physical meaning attached to it. So first, to find the acceleration, remember that the acceleration is the derivative of the velocity. Okay, that's what we know. So the velocity is nothing more than the antiderivative of the acceleration. That's the velocity. It means it's the antiderivative of 0.2 t dt, which is equal to, that's a constant, antiderivative of t dt. It means the velocity is 0.t2 times a half t squared plus a certain constant c. Okay, means the velocity is 0.1 t squared plus c. So if I know the acceleration, so I know the derivative of the velocity, I know the velocity. Now, of course, we have a constant c to work with, but I have initial condition. But v of 0 is equal to 0. It means if I plug in a 0 in here, so in this case, c is 0. So the velocity is 0.1 t squared. That's it. Okay. Now I need the position. So that's the first relationship. Now, what do we know? We know that the velocity, how fast the object is the derivative of basically where the object is at every moment in time. But that's the change. So the derivative is just basically intuitively is the change of distance over a very small change in time, which is going to give me the velocity. So the position is the antiderivative of the velocity. Antiderivative of the velocity. It means the antiderivative of 0.1 t squared dt, which is equal to 0.1, 1/3 t to the power 3 plus a constant d. Again, so s of t equal 0.1 over 3, which is 1 over 30, plus d. Again, the initial velocity at initially s of 0 equal to 0. So this gives me that 0 plus d is 0, d equal to 0. So the position is equal to 0.1 over 3, 1 over 30 t to the power 2. And that's where the object is at every moment in time. And this is really make the initial condition really makes sense to us, because if initially the object is not at 0, so the object is like 5 units away from 0, that's where initially it is, the position will change. So the position function in this case will not be a 30 cube, it's going to be a 30 cube plus another constant. So this is really where the initial conditions start really playing a role. Okay, let's look quickly at the other three and then we proceed. But we have
I have a question.
Yes, I'll back up.
So A would be like basically equal to f to the second derivative the
Yes.
V would be equal to the first derivative and
Exactly.
it will be equal to just F.
Exactly. That's the second derivative.
Okay.
Absolutely. That's the second derivative.
All right.
Ready? Good question. Let's see. Have a look at 49. I'm imagining all your questions are from section 4.9, right? Right? Okay. So 49 is, what this 49 is about? It's 49 from which section, Austin? 5.1. How about 73, Chris? 79. 79 is from which section? Okay, so I'll look at number 79. Sorry, I'm looking for it. And 79, they're giving me the derivative, which is 7x times x to the power 6 minus 1 over 7. And at 1, it takes the value 2. Again, so that's the same type of problem. So first, I need to find g. So I have now the derivative. I need to find the function. So it's equal to 7x times x6 minus 1 over 7 dx. All right. So see, this is equal to what? Equal to. Now, remember, I cannot break up this integral because there is a multiplication. As I said once before, and it's very important, we cannot break the integral in case we have a multiplication. We cannot really break it. So we have to manipulate. And the natural thing to manipulate here is basically to distribute. That's really about what we have. So 7x times x6 will give me 7x to the 7 minus 7x times 1 over 7 will give me the x dx. So I have no way out in this except distributing. So finally, this would give me antiderivative of that is 7 over 8 x8, because the n is 7, and this is a half x squared plus c, and that's my g of x. So now I have g. I'd go to my initial condition. I get 7 over 8. I plug in 1 plus c is equal to 2. Now common denominator, and we are done. So common denominator of 8, so that's give me a 4. So I will have 3 over 8 equal to 2. So c is 2 minus 3 over 8. 8 times 2, 16, which is 3 over 8 for c. And this would give me g of x equal minus a half x squared plus 13 over 8. End of the problem. All right. Okay. So now we look at 49 and then we move on. So I look at 49 in section 5.1. Okay. Now, I see a lot of problems, but I will definitely not do all of them. I will just pick 2 just to make sure we understand the notation. So I have a sigma k equal 1 to 10 of k. And they want me to evaluate. I'm not going to add them. We're just going to understand how to read them. Okay, so how to, so sigma, it means we're adding stuff. So that's what sigma is. What are we adding? If k is 1, I plug in 1 in here, I get a 1. Plus, if k is 2, I plug it here, 2. If k is 3, I plug it, 3. And I keep going, 4, 5, 6, 7, 8, 9, and the last one is 10. And then the rest, you just pick up your calculator and add them, okay? I'll do another one. Suppose I have sigma j equal 1 to 3 of 3j minus 4. So I'm doing letter F. Okay. Again, let us just expand it. So sigma, it means I'm adding stuff. What am I adding? Okay, I take j equal to 1 because that's what we're starting, and we plug it in here and see what we get. So I will get here for j equal to 1, 3 minus 4 plus j equal to 2. I will have 3 times 2, 6. I'll get 3 times 2 minus 4. And then j equal to 3, I get 3 times 3 minus 4. So finally, I'll get minus 1 plus 6 minus 4 plus 9 minus 4, which give me a 5. All right? And everything along those lines later on. So one more, and I definitely have to stop. Suppose they gave me, so I'm looking at this one, sum of 2p plus p squared, and my p go from 1 to 5. Okay. So it's the same idea. It's a sum of stuff. And we read them. If p is 1, I plug in p in here. I will have 2 plus 1, 2 plus 1, 3. If p is 2, I plug it here. 2 times 2, it's a 4. 4 plus 4, I get 8. P equal to 3, plug it. 2 times 3, 6. I have 6 plus 9, which is going to give me a 15. P equal to 4, then I will have 2 times 4, 8. 8 plus 16, that's going to give me 24. Give and take a stupid mistake. And finally, P equal to 5. I will have 10. 10 plus 25, give me 35. And then you evaluate. Okay, so that's really how we read the sigma notation, which is absolutely important for us. Right? Okay, so today what we're going, before I move on, I'll keep it for a second in case you guys are writing your notes. So today we're going to start talking about approximating area. Okay, so let us see what do we mean by approximating area. Okay, the easiest shape, before we start, the easiest shape people can actually evaluate is the area of a rectangle. So the area of the rectangle, you can, it's the length if you want, times the width. That's so areas. That's really our problem today. Okay, so which is L, that's the length, times the width. Very good. That's the easiest one because, okay, how many unit I have, how many unit I have. So we have to multiply the number of unit here by the number of unit here. It gives me the length times the width. Simple problem. If I have a triangle, again, the problem was solved easily, and it was a half base times height. That's a triangle. Okay. So these are the two basic shapes. Now let us say I have something that looks a little bit more complicated, something like a pentagon like that. So how do people compute this kind of shape? Again, they say, you know, we can split it into triangle. They split it into triangle. They know how to compute the area, the area, the area, end of the picture. The problem came here. The problem came when people had circles. That's where the issue came. And what the issue here is because we have curves. So the question is how to compute the area of this circle. Okay, and that's the center. All right, that's this complicated problem. And the way they did it historically, I mean, that's actually the way they did it, is they don't know how to compute the area of a circle because it's curving. So they said, let us approximate it by something we know. So what they did is, and that's exactly what they did, and they took this and split it into pieces, a lot of pieces, okay? And they connected those lines. So they want to create something not curving. They connect. That's historic what they did. And then they computed the area of those triangles and added them. So it was a lot of work. So that's how they came up with the area of a circle. Now, those are simple triangle. They knew how to compute them. Okay, but then they said, the more subdivision we take, the better approximation we did. And indeed, that's what they did. So they start approximating by smaller polygon. So the idea is the idea of approximation. We don't know how to do something. We approximate it by something we know how to do. And they filled it up with smaller and smaller triangle, and they were able to somehow find the area of a circle. So the problem with the circle is that it's curving. That's really a main issue. So here comes our problem. So our problem today is the following. Suppose you have a function. So how mathematicians start now trying to generalize the idea. And a function, and that's the graph, which curves. Curving is the problem. It's this curvature. If my function is constant, okay. Sorry, now I come back. So that's the function. And this is a point A on the curve, and this is a point B. And the question is, if I know the function, I know the rule that for every x give me the output, how can I find the area under the curve? What's the area? Okay, so if the function was constant, I don't have an issue. The area under curve, this really become a rectangle, so there is no issue. But the issue is this curving. This curving makes the problem really, really hard. So the idea is how to do that. And usually in math, when we don't know how to do something, we actually approximate our problem with something we know how to do. So the idea was, this is hard. So the idea is let us approximate it with a bunch of rectangles. So let us fill this curve under it with rectangles. And we're going to make this actually very precise in a second. We're going to fill it with rectangles. The more rectangles we can fill, the better the approximation. And instead of finding the area under the curve, we're going to start finding the area of the rectangles. Why we can do that? Because we know how to find area of a rectangle. So we will be able to find the area under the curve. So they approximate it, and that's the only way out. So approximation is the only way out. And this will be one of the crucial ideas of mathematics that we're going to encounter now and later on. If we don't know how to do something, we approximate it by something we know how to do. And that's how the area is done. Okay, so we're going to elaborate the process by an example because it's a much easier way to do. So here we are. We have the following example. So I'm going to take a fairly simple curve. And my question is, estimate the area under the graph of the function f of x equal x squared between x equals 0 and x equal to 1. Okay, so we're going to do the following. So this is my function. I'm going to try to draw as. So that's my function, f of x equal x squared between 0 and 1. So this is f of x equal x squared. This is 1. And that's my function, f of x equal x squared. And I need to approximate the area under the curve. And we're going to approximate it in 3 different ways. The first way is I'm saying using right end point with 4 subdivision. All right, doesn't make sense to you at all. Let me make sense out of it. So the idea is we're going to approximate it with rectangle. So the first thing we're going to do, I'm going to approximate it with 4 rectangles. What does this mean? I'm going to take the interval 0, 1, and I'm going to subdivide it into 4 equal pieces. 4 equal pieces. So we're going to divide 0, 1, the interval 0, 1, into 4 equal subinterval. Why 4? Because I told you I want 4. Okay. And I'm going to call delta x the length of each subinterval. The length of each subinterval means delta x equal. Now the length of the whole is 1. If I divide it in 4 pieces, it's going to be in this problem 1 over 4. Okay. Now, what kind of rectangle we're going to do and what the word right is in this picture. I'm going to do the following. So first, let us figure out what those are. If this is divided into 1/4 and this is 0, it means this point is 1/4. And this is point is 1/4, that's a half. And this is 3/4. Okay. So the rectangle are the following. I'm going to take a rectangle, which is the base is this, that's the base. And the height is the value of the function at the right point of the interval. That's my first rectangle. That's my first rectangle. Let me find the area of this. The area of this rectangle. What's the area? It's the height of the rectangle times the width. So it's the height times the width. That's the area. Now, but what's the height of this rectangle? The height is from here to here. And this point here is nothing more than 1/4, the value of the function at 1/4. So the height is nothing more than the value of the function at 1/4 times the width, which is my little delta x here, which is 1/4. So that's the area of the first rectangle. Then I'm going to take the second rectangle, exactly the same. I'm going to take for height, so that's my second rectangle. Okay, and the height here is from here to here. It's the value of the function at 1/2. Okay, these are the rectangles that I'm going to use. So the area of this one, the area is the value of the function at 1/2 times the base. So it's the height times the base. Okay, then I'm going to keep doing. I'm going to take another rectangle. Again, I'm going to take for height the value of the function at the right point of the interval. And I have my rectangle. Okay, that's my third rectangle. And finally, my last rectangle. I take for height the value of the function here. So that's my height. And the width is from here to here. It's the delta x. And that's my last rectangle. Okay, so these are the rectangle I'm going to use to approximate. So let's write down this. Okay, now some notation in order. The endpoint of those subinterval, in general, we're going to call them the following. The first, we're going to call it x0. And this, we're going to call it x1. This, we call it, we'll just give them name, x2, x3, and this we call it x sub 4 because this notation is used a lot. All right. So we're gonna call R4 to be, and I would give R4 a name, to be, or the sum of the rectangle, the area, sorry, let R4 be the sum of the area of the rectangle in the picture. Exactly. In the picture. Okay, so let R4 to be that. What was the area of the first rectangle? We're going to repeat right now. What was the area of the first rectangle? The height is the value of the function at 1/4. The width is from here to here. So it's going to be the value of the function at 1/4. That's the height times the width. That's the first rectangle. Okay, plus what's the area of the second rectangle? It's the value of the function at 1/2 times the width, which is 1/4. Plus, what's the area of the third rectangle? The height is the value of the function at 3/4 times the width, 1/4. What's the area of the last rectangle? It's the value of the function at 1. So it's the value of the function at 1 times 3/4. Okay, so height width, height, width, height, width, height, width. Okay, Chris, make sense? Okay, let's keep going now. What's the value?
Yes, thank you.
Yeah, what's the value of the function at 1/4? Let's go back. What is my function? My function f of x is x squared. So the value of the function at x4, I know what it is because I know the output here. So f at 1/4 is going to be 1/4 squared times 1/4 plus the value of the function at 1/2. I know it because I know what's the output at 1/2. So it's going to be 1/2 squared times 1/4 plus, what's the value at 3/4? Again, it's the value of the function, which is times 1/4 plus f of 1 is the value of the function at 1 times, oh sorry, that's 1/4, times 1/4. Height, width, height, width, height, width, height, width, crucial. And then I pick up my calculator. Because at this stage, I just compute those numbers. And I think I did that. And we're going to get 0.46875. Okay, and that's the value we get. This is just by adding no more dollars. Okay, now the actual area, is it more or less than that? So the actual area. So that's what we get by doing an estimate. So now what's the actual area? Is it less than that? So the actual area, is it more or less than our estimate? Just by looking at this picture in this particular problem. Is the actual area more or less than our estimate, which is the sum of the area of this rectangle? Definitely less. No. Less than our estimate? Is she right? Absolutely so, because the area is this. When we're estimating, we're taking the sum of the area of the rectangles. There is all those extra we are taking off. All right, so the question is, how can we improve on that? So we know that this is really far from the actual area because we have all those extra little things that we're dealing with. So how can we improve on this estimate? Ideas? How can we improve?
Well, I was thinking for the rectangle, we could maybe just take it as a triangle, but because it seems like it's a straight line right there.
Where is this? That's not a straight line.
Oh, okay, then
That's a f of x equal x squared. This is not a linear function. It's curving.
All right, then.
Yeah, I tried to write. I wanted a big picture, so it seems like a line. It's the x squared. It's not a line by any stretch of the imagination. So how are we going to improve on this estimate?
We can add more subintervals.
We have to add more subintervals. Absolutely. There is no way out. So we can divide into 8 subintervals. Okay, so I'm going to do that, and that's probably the last time I will do that. It will be up to you. So now we're going to improve on the estimate. How we're going to improve on the estimate? More like I did for the circle, more subdivisions. We're going to fill it with more rectangles. So improve. It's the same problem. You can look at this part A and then part B if you want. It's the same problem. It's the same function. Now I'm going to do estimate. So B, we're going to do estimate using right endpoint. And then I'm going to talk about left endpoint, and then you understand what the right mean here. Right endpoint with, let us say, 8 subdivisions. Okay, so now I'm going to make more subdivisions. So this is, I'm not changing, of course, the picture. I'm just going to make it a little bit like that. So this is, remember, that's curving, that's x squared curve. The only reason it looks like not curving because I'm drawing it large. So this is my 1. And now 8 subdivision. Now when we do 8 subdivision, and usually we take them equal subdivisions. So now we're going to divide my interval into 8 subdivisions. Okay. And what's the delta x in this case? What's the delta x? The delta x is the length of every subdivision. So it's the length of every subinterval. And what's the length of every subinterval in this case? The whole thing is 1. If I divide into 8 equal pieces, the whole thing is 1 divided by 8. So now we're going to do the tedious work of dividing it by 8. So this is 8, 8, 8, 8. So 8 little pieces. And now we're going to take the following rectangle. So this is 1 over 8, 2 over 8, 3 over 8, 4. So it's 1 over 8 because I'm starting at 0. That's important. 4 over 8, 5, 6, 7, 8 over 8. These are my intervals. All right. Now what are the rectangles? Here are the rectangles. At 1 over 8, that's the right point. The height is the value of the function. The width is always the delta x. First rectangle. Second rectangle. The value of the function at the right point. And the width. Okay, and then I keep going. The value here. The value here. So it's a little bit tedious, but that's the last one I will draw. The value, they should be equal to delta x. The value and the value. Okay, so the rectangles are this one, my rectangle. And as you can see now, the error is less. So we're having a better approximation and we're filling it more and more. So these are my rectangle that I'm going to use. So now we're going to call the area. So R8, R stands for right, 8, is the sum of the area of the rectangles in the picture. Sum of area of rectangles in the picture, as simple as that. So each one of them has for height the value of the function at the right end point, for width delta x. So let us see this is equal to what? What's the sum of those areas? Very good. It's the value of the function at 1 over 8 at the right point. So here, the area of that is the value at the right point, which is 1 over 8 times, so that's the height times the width, which is 1 over 8 in this problem. So it's going to be the value at 1 over 8 times 1 over 8 plus, I mean not to write the whole sum because it's tedious, at 2 over 8 times 1 over 8. And then I keep repeating at 3 over 8. So I'm really adding a lot of stuff. I'm adding the area of 4 rectangles at 4 over 8, at 5 over 8, at, remember, height, width, height, I repeat because I'm adding 1 over 8, so times 1 over 8, and finally 1 times 1 over 8. And then I have to add them. Okay, now let me add them. What's f at 1 over 8? Do we know the value here? Quickly. F of 1 over 8 is what? Quickly, I want the answer. I'm working with the same function, which is fx equal x squared. So what's f at 1 over 8?
1 over 64.
Right, it's 1 over 8 squared, right? What's this? 2 over 8 I know it's 1/4, but square, that's the output. 3/8 square. So you keep adding, It's tedious, but that's not the problem. The problem is to know what we're doing. So if I keep adding, I'm gonna get 0.3984, which is gonna give me a better estimate for the area. So the idea now, okay, that's really the concept. So the third question would be, can I do better? Yes, I can. And how can I do better? By taking more and more subdivisions. I can take 20 subdivision, 30 subdivision, 40 subdivision. But the question is, when do we stop? Okay, we stop. Actually, we never stop. But when we start realizing that as we take more and more subdivision, the areas are becoming very, very close to another, that's when we say, you know, we are almost there. Okay, that's really the idea. So let me show you a little bit what happened when we take more and more subdivision. So you'll be convinced that we're actually covering the area. So I'm going to try to share the screen here with us. And what do I want? I want this one. Okay, so this is the picture. This is x squared. That's my function. My interval from 0 to 1. And I'm using 8 rectangles. So that's the rectangles I drew. And I'm taking, sorry, I took the right one. So this is the rectangle we drew in class, right? That's the one I just did on the board here. And the area here, they give us the estimate area. This is where I picked up my number, which is the 0.3984. And that's the actual area, which is 0.33, which is we're going to compute next week. Anyway, now let's see if I take more subdivision. Suppose I take 20 subdivision. I want you to see the plot. So if I take 20 subdivision, you realize we're covering the region more and more. So the sum of the area of my rectangle are not equal to the area under the curve, but the error is actually decreasing. The error is those extra little triangle on the top. So we can take more subdivision because, so let me take 100 subdivision, for example, okay, and replot. I want you to see what happened here. When we take 100 subdivision, the sum of the area of the rectangle, which we can barely see, is becoming fairly, very close to the area under the curve. And we can improve, we can take more, and realize I don't have to do any computation. We can just pick up the answers from here. So one more. Now you can see, you can barely distinguish the sum of the area of the rectangle with the area under the curve. Okay, that's really the idea. So to compute the area, we just have to be approximated by the sum of the area of the rectangle. And that's the picture. That's exactly the picture. All right. So some names before I proceed any further. Names is the following. Yes? Question? Okay. Name, a little bit of notation, the following to prepare for the general setting. This is, as I said before, usually we call it x0. And this usually we call it x sub 1, x sub 2, x sub 3, x sub 4, 5, 6, that's a subscript, 7, and this we usually denoted by x8. A notation that I will be using, probably not today, but next time we have to be used to it. And R8 is called R8 or R4. We call it right because we use Riemann sum. It's called right Riemann sum. Very good. So now the second question is, why did you take the right point of the interval? Why did you take for height the value of the function at the right point? And the idea is, there is no reason I took that. I can take for the height the value of the value of the function at the left-hand point. And that's what we're going to do now. So question number 2 is the following. It's the same thing, but I'm going to take the left endpoint. So question number 2 is estimate the area under the graph of f of x equal x squared. Again, we're going to estimate the area using, instead of right, we're going to use left endpoint with 4 subdivision. Okay, with 4 subdivision. Now, what's the difference here? The difference is not, instead of taking the value of the function at the right point, we take the value of the function at the left point to do the subdivision. So here we are. My function is the same. Nothing changed. F of x equal x squared. This is 1. I want 4 subdivisions. Means I need to divide into 4 equal pieces. So my delta x here is 1 over 4. Left endpoint means the following. The rectangle that I'm going to take half, so this is 1/4, a half, 3/4. So I'm going to do the same estimate. But instead of taking for height the value of the function at 1/4, I'm going to take for height the value of the function at 0, at the left endpoint. So in this particular problem, the value here at 0, so I say, okay, my rectangle consists of a line. My second rectangle is going to be the value at 1/4 for height, and the width is always 1 over 4. That's my rectangle. Then my third rectangle. So this is the height here. This is the height. And then I'm going to take for height the value at the left endpoint, and for width, the value here. That's my other rectangle. That's the height. For my last rectangle, the height is from here to here. That's the height, the value at the left endpoint of the interval, and the width is always 1 over 4. And this is my last rectangle. Okay, so instead of taking, let's contrast those two. The right endpoint, I take for height the value at the right endpoint of the interval. And then the width is always the same. At the right endpoint, the width is the same. The width is the same at 1. In the left endpoint, instead of taking the height, the value of the function at the right, I take it the value at the left. Because f of 0 equals 0, so I just get a line, just by coincidence. And then that's the height, and that's the height. And we're going to call L4, which we're going to call the left Riemann sum, L4, which we call the left Riemann sum, is the sum of the area of the rectangle in the picture. Okay, and let us see what's the area. Okay, the first rectangle, the area is f of 0. Now I know that f of 0 equal to 0, but I'm going to write it because we have to get used to this idea, times the width, plus the value of the function at 1 over 4. The area here is the value at the left point times the width. That's my area. So it's f at 1 over 4 times the width. Very good. Plus the value at, I look at my picture, 1/2 times 1/4. I'm picking up this one. That's the area here. That's the area here. Plus, now I want to pick up the area of the last one. It's f at 3/4 times 1 over 4. And now it's just a matter of computing. F of 0, it's 0 squared times 1 over 4 plus This one is 1 over 4 squared, because that's my output, times 1 over 4, plus this one is 1/2 squared, times 1 over 4. So it's the same idea. It's absolutely the same idea, but we're changing the point that we're using for the height. And this is 3 over 4 times 1 over 4. Now, again, we're going to add those. And I forgot to pick up the value here. It will take me 1 minute. So I'm going to share the screen because I forgot to find the exact value. The right, now I'm using the left, I'm replotting. That's the picture I'm trying to grasp. So the value at the left end point times the width, left end point width, left end point width. So, and the sum of the area now is going to be 0.21875. Okay, and that's really going to, and that's definitely an underestimate. So it means the actual area is larger than that. Just the picture tells me that, okay? And now we can repeat the same thing as before. The more subinterval, the better the approximation. So if I get, let's say, 20 subinterval, and then I get a better approximation because we're filling up the curve more. So I'm always taking for height, the value at the left end point times the width, left end point width, left end point width. And then I can repeat the same and the same process. And I keep asking myself, okay, what's the estimate getting close to? What's the estimate getting close to? Then I realize they are getting close to a kind of a fixed number. And this fixed number will be actually the area I'm looking for. Okay. All right. Very good. So we're estimating. So the last question is, I'm taking left end points, I'm taking right end points, and the question, can I take other points? And this leads us to the last idea here, which is the following. So, but before that, L4 has a name and L8. So L4 is called left Riemann sum. It's called left Riemann sum. Okay. I don't have time to do the last idea, but I definitely want to talk a little bit about the numbers. So this is the left, this is the right. So we compute those. If I take 10 subdivision, I get 0.285, 0.385. 20 subdivision, 0.308, 0.35. 100 subdivision, 0.32835, 0.33825. Realize the numbers now are getting close to each other. 500, 0.332, 0.3343. So as we take more subdivision, the areas, according to us, the actual area, according to those numbers, I'm not going to make up any numbers, is becoming close to what? 0.33, 0.33. I don't have a great estimate, I can do better than that, but according to the number I gave you, the actual area seems to be getting closer to 0.33. Okay, because the left and the right, whether I take the right or I take the right or the left, my numbers are getting close to 0.33. So it means the area is getting close to 0.33. If I take more subdivision, I will get a better estimate. More subdivision, the better estimate. And it depends on my computer capacity. The last idea is, I'll take briefly about, I hope you can understand it. If not, I will take it up back again. The last idea is we can do the same problem. The same problem. It means estimate the area, but now, so this is, but now estimate the area under the graph of fx equal to x squared using midpoint with 4 subdivisions. What are they talking about? What are they talking about? Midpoint. Okay, that's what they are talking about. Again, my same function. That's my function. 1. Okay. Again, I'm going to divide it into 4 equal subintervals. Okay. But now midpoint means, listen very carefully. I'm taking for height the value of the function halfway into the interval. That means I take the interval 0, 4, and I take the value of the function here as a height. And the width, I do not change it at all. That's my width. So the height is the value of the function at the midpoint of every subinterval. Again here, I take midpoint and I take this for a height. That's the height. But the width is always the same. So the base of my rectangle are not changing from the left and the right. The only thing changing is the height, which is the value at the midpoint. So that's really my height. So there are several ways of doing this problem. Again, this is my height, midpoint. That's the height. The base never changes. That's the base. So the base never changed, but the height is actually changing. My height is actually changing. Again, base doesn't change. The height is the value here. So that's my height. So that's really the midpoint. So it's not really hard, but you have to know that the base doesn't change. That's the base. The height is the value of the function at the midpoint. That's the midpoint. Now, very quickly, we can do that if you guys can help me so you can do your homework. What's the coordinate of that point? What's this? What's this? What's this? If this is 1/4, how much this should be?
1/8.
1/8. That's 1/8. This is, if you want, 1/8, 1/8, if you want. So that's 2/8. This is going to be 3/8, 4/8. This would be 5/8, 6/8, 7/8, 8/8. And what is M4? M for midpoint, 4 for the number of subdivision. Now, and I will be done. It's the value, the height is the value at the midpoint. It's the value at the midpoint. The width never changed, is 1/4. Now, plus, the height is the value here at 3/8. The width never changed. The height is the value at the midpoint. The width never changed. The height is the value at the midpoint. The width never changed. So the midpoint is, instead of using the left for height or the right for height, we use the midpoint halfway through for the height, but the base never changed. It's the same rectangle. And now I just have to take and compute that. So this is going to give me 1/8 square times 1/4. 3/8 square times 1/4. 5/8 square times 1/4. And finally, 7/8 square times 1/4. And the rest is actually computing those numbers. And I will give you the number, and definitely I have to. So I'm going to go back to my picture, and I'm going to take 4 subinterval. That's exactly it. And then I'm going to take what we call the midpoint. And I'll show you, that's the picture we're trying to show. The height is the value halfway, 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 halfway. And the estimated area, if we can read it well, is 0.328125. It's just by adding those values. Okay. All right. So that's the midpoint. So we take halfway in between. So far we have 3 ways of estimating the area. We can use left point, we can use right point. And each one of them is important for us to know the difference, or we can use the midpoint. Now, which one do you think is the best? Left, right, or midpoint?
Midpoint.
Any question? What?
Midpoint.
Midpoint. Why? Because watch what's happening here. We're losing some area, we're compensating it. We lose and we compensate. We lose and we compensate. We lose and we compensate. Left and right are almost equal in terms of how good they are, but the midpoint is usually better than both left and right. Okay, and M4 is called the midpoint Riemann sum, like we call the other right Riemann sum and left Riemann sum. Right? So I stop right here. Please do your homework for Monday. We still have 2 weeks and we have to learn a lot in this week because I have to compensate the time I was away. So we have to work very hard so I can get you very ready for 164. So you guys have to work with me very well. And have a wonderful Thanksgiving break. You guys have any questions? Any questions before we go? All right. Bye-bye.
Have a good Thanksgiving break.
Thank you. Bye-bye, guys.